Hi there, welcome to my next video on the Physics Aptitude Test, where I'm going to be speaking about electricity and magnetism. So the first thing with regard to the syllabus that I would like to address would be some terminology, some key terms that you will need to be able to understand. Firstly, current is a word that you'll obviously come across quite a lot when tackling circuit questions. And you should know that this refers to the flow of positive charge. So it's not the flow of electrons, it's the opposite direction to the flow of electrons. Next, voltage. I think different people think about voltage in different ways. Another word for it would be potential difference. But the voltage over a component would basically refer to how much the potential energy has dropped from before the component is used and after the component is used. Charge, this is such a weird one to describe. I feel like most people have an intuitive idea of what charge is, but it's essentially a property of matter which causes it to experience a force in an electric field. Resistance describes the slowing of the flow of electrons or current. It's up to you kind of which way around you think of this due to particle collisions. Energy, again, is like technically a really hard term to define or describe, but the way I like to think of energy is a sort of like transferable fuel that can make stuff happen. And then power, much more simply to describe, it's just the rate of energy transfer. And some other important things that you'll need to know are some circuit components. So wires, I'm sure you're aware that the symbol is just kind of like a straight line in the circuit. This is just a medium for your current to flow, and an ideal wire has zero resistance. A battery would be the source of the energy for a circuit from a chemical source, and its symbol will look something like this, or a cell could be something like this, with the long side represents the positive side and the short side represents the negative side. And then a resistor has a circuit symbol like so. It's essentially a high resistance material to impede current flow, and slow it down to cause a potential difference. You can also get variable resistors as well, which will have a symbol like this. And it just means that you can change the resistance of the resistor manually. A filament lamp, basically just a lamp, a light source, which causes a drop in voltage. Diodes, they allow current to flow in one direction only and impede current flow in the opposite direction. Symbol for the lamp like that. Symbol for the diode is something like this, where it will allow current to flow in this direction only, in the direction that your kind of triangle points. A capacitor, I don't have room to do the circuit symbol for capacitor, but it looks like this, if you can see that. And they're essentially two parallel plates that can charge and discharge. So if you send a current down a circuit and it comes to a capacitor, then the charge will build up on one side. And then once you stop fueling this capacitor, essentially, or if you change your circuit paths, then your capacitor will discharge and then act kind of as a battery that's discharging. Kind of. I say that liberally, but it will send a current background. An LDR is a light dependent resistor, and this is a resistor, kind of a variable resistor, except rather than manually changing it, it changes automatically depending on light conditions. So for example, if it's brighter outside, then the value of resistance will be less. And if it's darker outside, then there'll be a higher value for resistance. And then finally, we have a thermistor, which is kind of a similar idea to the light dependent resistor, except it's a temperature dependent resistor. And depending on whether it's a negative temperature coefficient or a positive temperature coefficient, then it changes which around it is. So for a negative temperature coefficient, that would mean if the temperature is higher, then the resistance will be lower. And vice versa. And for a positive temperature coefficient, if there's a higher temperature, there'll be higher resistance, and lower temperature, lower resistance. And a symbol for a LDR would be something like this. And then the symbol for thermistor would be something like that. So here I just have a very simple example of a question where they're asking for a range of temperatures around room temperature and above, sketch how the resistance of the following components may vary with temperature. And the first one is an ideal wire. And if you remember what I said about an ideal wire, the resistance is always 0. So whatever the temperature is, we'll have a 0 resistance. And then for a filament light bulb, as the filament bulb gets hotter, there's more particle movement and more resistance. So the resistance will increase with temperature. And then finally, a thermistor. Now, it hasn't been very specific here, but most of the time when they say thermistor, you can assume it's going to be a negative temperature coefficient. So it'll be the opposite way around, where we start with initial resistance, and then as the temperature increases, the resistance becomes less. Okay, so the next topic refers to transformers, and this may or may not be something that you've come across before in school, but essentially what's happening is that we have these two coils that affect each other using magnetic fields, but again, you don't really need to know any of this to tackle any of the questions. But essentially, the number of coils causes either a drop or a step up in voltage between the primary side and the secondary side. And if we look at power conservation, then we can see that if we have a primary voltage source VP and a primary current IP, on our opposite side, if no power is lost, so assuming no energy loss, then we should have this power here equal to the power on our secondary side, which would be Vs, our secondary voltage, multiplied by Is, our secondary current. And then from our definition of the transformers ratio, our ratio of turns in our coil is equal to the ratio of our voltages on the two sides. So our secondary voltage divided by our primary voltage will be equal to the number of turns in our secondary coil divided by the number of turns in our primary coil. And this is essentially all you really need for most of these transformer questions. If you've not studied transformers before, I would recommend finding a YouTube video or something just to kind of get your head around the physics. But as for answering the questions, this is likely all you need. But I can't guarantee that. So please, if you haven't studied it, do some research. So this question asks, an ideal transformer has 100 turns in the primary coil. It is connected to an alternating supply of 100 volts, 2.4 amps. How many turns are required on the secondary coil to supply 4.8 amps? So I've just popped this all-important equation down here, and I just have a little sketch of what's happening. And here I've put in the information that we're told. So we're told that the primary voltage is 100, our secondary current is 4.8, our primary current is 2.4, and then the number of turns in the primary is 100. And the information that we want is the number of coils in the secondary. So truthfully, we can just neglect this information here because we can use this side of the equation to get all of the information that we need. And after doing a bit of rearranging, we see that the number of turns in the secondary is 50, which is the answer to B. We have a very similar question here. I would encourage you to try this yourself first. It asks, the primary coil of a transformer is connected to an alternating voltage supply of 240 volts and draws a current of 1 amp. So this is on the primary side. And then the secondary coil is connected to a resistor and delivers 120 volts. If there are 50 turns in the primary coil, how many turns are there in the secondary coil? So again, I've just popped in that all-important equation and then popped in the numbers that we know. So we know that our primary voltage is 240 and our secondary voltage is 120. We don't know our secondary current, but we know our primary current. And we know the number of turns in the primary, but not on the secondary. And what we want is the number of turns in the secondary. So we need this ratio here. And we also have information about this ratio here. So we can equate these two, rearrange, and get an expression for the number of turns in the secondary. And it happened to be 25, which is optimistically answer C. Right, so the next portion of the syllabus relates to parallel and series circuits. I'm sure you all remember from GCSE the rules about adding resistors in parallel and series, and how current splits in parallel, but it's the same along an entire branch in series, and that voltage splits in series but stays the same in parallel. And for some, you may have learned this as Kirchhoff's voltage law and Kirchhoff's current laws. But yeah, just bear these in mind as you answer these questions. So this question here is another multiple choice. It says that two resistors are connected in series with a potential difference V across them. And we need to work out the power dissipated in the resistor R1. So we've been given a lot of information, but unfortunately we've been told that the voltage is across the two resistors, which means that it's split between them because they're in series. So unfortunately, it's not as simple as just saying that P is V squared over R, because the voltage across R1 is not V. So some other information that we might find useful is the current, because this is the same over the two resistors. So the first step that I did was write out the equations for power. So we have P equals IV, which we're not going to use because we don't know what V is. P is V squared over R, which we're not going to use because, again, we don't know what V is. So that leaves us with P equals I squared R. But that means that we need an expression for I. So in order to find the current in the branch, we would use Ohm's law, V equals IR. So we need the total resistance, which is R1 plus R2. And then if we multiply that by the unknown current, then we get the known voltage V. So if we rearrange that, we can get an expression for I as V over the sum of the resistors. And then we can just stick that I into P equals I squared R to get an expression for the power. And that answer is the same as A. Okay, so next we are given a question about capacitor. And this requires us to know a few equations about capacitors. And if you've not studied capacitors yet in school, then I'm hoping through these questions we will have tackled a lot of the equations that you need to know. But this question says we have a capacitor of capacitance 3 nanofarads. Capacitance describes how capacitive a capacitor is. I suppose in a similar sense to how resistance describes how resistive a resistor is. So you don't really need to deep what capacitance means too much. It's just helpful to know what the equations are. So they told us the capacitance is 3 nanofarads, and it's charged to a voltage of 10 volts, and they want to know what the charge held by the capacitor is. And the first important equation that we need to know about a capacitor is that Q equals CV. So charge is equal to the capacitance multiplied by the voltage. And luckily, they gave us the capacitance and the voltage, and they wanted the charge. So we just multiply these together to get 3 times 10 to the minus 8, which is answer C. So here we have a question about adding resistors, and they ask us to do a few different things. So the first part A, we're asked to find the total resistance between node A and node B. So we need to do some resistor adding in parallel and in series. So I found the easiest way to handle any questions like this is to add up the resistances of each individual branch. So I have branch 1, branch 2, and branch 3 down here. So our total resistance of branch 1 is super easy. It's just R. Our total resistance of branch 2 is also pretty easy. We have 2 resistors in series, so that would be 2R. And then the third one is slightly more complicated. So the first thing we want to do is add these two in parallel. And for that, we have the reciprocal of 1 over R plus 1 over R. So 1 over R plus 1 over R is 2 over R. And then we take the reciprocal of that, R over 2. So this value here is R over 2. And then this value here is R. So if we add these together, we end up with 3R over 2 as our bottom branch's total resistance. So next, we need to add each of these individual branches in parallel to each other. So we take the reciprocal of all of their individual resistances, add those reciprocals, and then take the reciprocal at the end. And if you forget to take a reciprocal, it will be obvious, because if you have an R on the bottom, that means your units are wrong. Your units of R are ohms. And say I ended up with 13 over 6R, you know that's got to be wrong, because that would be not in units of ohms, that would be in units of ohms to the -1. So that's just kind of like a foolproof way of checking, which is why it can often be helpful to leave things in symbols until the end and then put numbers in. Okay, so we have an answer there. And then part B asks us, if potential difference of V is applied between A and B, calculate the power resisted in the resistor between B and D. So we have a total voltage of V. So the voltage across this branch is V, the voltage across this branch is V, and the voltage across this branch here is V. And we want to know what the power dissipated by this thing is. So in order to do that, we have a similar kind of approach to what we had in one of our other multiple choice questions, where, okay, so the voltage across these two components, if we take the parallel components to be one thing, the voltage of both of them together is V, but individually is not V. But we do have information about the current, because the current across the two components, component 1 and component 2, are the same. So we want to work out the total current of that line first. And that would be the voltage of a branch 3, V, divided by the total resistance of branch 3, which is 3R over 2. And now that we have an expression for the current, we can stick that into the equation that we had previously, P equals I squared R, where I is the current over that component that we wanted to know the power of, which is the same as the current along the whole branch, so that I that we just worked out. And then this R is the resistance of that one component, which is R. And then when we stick that into that P equals I squared R, we get this expression here for the power. So part C of the question wants us to calculate the total resistance between C and D this time, where C is here and D is here. So we're going to have to do a bit of a redraw to come out with an expression for that total resistance. And redrawing can be quite a difficult skill. For me, it can take like several redraws to get it right, but I have a few tips to help with redrawing. So the first thing I like to do with redrawing is coloring in. And you may not understand what I've used each color for here, but essentially what I've done is every point where the voltage is the same, I've given it a color. So the voltage across all these bits over here along this kind of thread of wire is going to be the same. And then only when it reaches a component will it drop. So it reaches a component here. So all of this voltage is the same here. And then at these points, they meet components. So it meets a component here and it drops there. And it meets, the voltage is the same along these two branches and then drops as it goes over these components. But the drop is the same because the resistance of these two are the same. And then we have a different kind of voltage level here. And then we can, and I've also numbered the resistors so that I can keep track of which resistor is which. And now we just need to go ahead and try and do a first redraw. So for this, the rules are you need to make sure that each resistor has the same colors on either side as what they were in your initial drawing. And then your redraw, your goal is to try and find something where it's obvious what's in parallel to each other and what's in series to each other. So this first redraw, it's not obvious what's in parallel and what's in series to each other yet, but we can see that these two are in series and these two are in parallel. So these are some things that we could simplify down straight away if we wanted to, but I sense I didn't do that in my next redraw. So for my next redraw, I shifted this 6 backwards to show that that was in parallel there. and then I shifted this one here forwards, and I shifted the D and C nodes to show more clearly that they were the input and the output, essentially. But at this point, we can easily see that these are in series and these are in parallel. So we can shift those down. And at this point, I decided to get rid of my numbering as well, because I wasn't going to be moving things around too much anymore. So at this point, we have a value of R here, a value of 2R here from the 3 and the 2 being added up, a value of R over here from resistor 1, and then we have a value of R over 2 from these resistors in parallel being added up. And down here, we can see that these two are in parallel to each other. So my next, well, you don't have to redraw at this point. I think it's quite clear. But if you were to redraw again, then you could simplify these two down. So my next redraw, I've added these up in parallel to get 2R over 3. And here we can see that this top branch here now is solely that resistance R. And then we have our 2R over 3 plus an R over 2. And we can add those two up to get 7R over 6. And then in our final redraw here, we can see that we have two resistors in parallel that can just be added like two resistors in parallel normally. So we have the reciprocal of R here plus the reciprocal of 7R over 6, add them together, and then take the total reciprocal to get 7R over 13. And that is our final answer. So this next question is kind of like a bridge question, and some of you may not have seen things like this before. You can Google Wheatstone Bridge if you'd like. That is, you can Google Wheatstone Bridge if you've not come across anything that looks like this before, and maybe find a YouTube video that can describe what's happening with the Wheatstone Bridge. But essentially, we can take that kind of same method again of the drawing where our voltages are. So everything along this branch here is 84 volts. And everything along this branch here is 0 volts. These four have the same resistance of 12, I believe. And then these three have the same resistance of 6. So the first thing that should strike you here is that we have symmetry. And if we have symmetry, then it means that the voltage drops across the components are going to be the same. And what I mean by that is, for example, because these are both worth 12, they will have the voltage of 84 will be split equally between them. So the voltage over this component here will be 42, and the voltage over this component here will be 42 as well. And the same thing goes for B and C down here. The voltage over here is 42, and the voltage over this one is 42. But that also means that our voltage drop here is the same as our voltage drop here. So that means this component here, A, there is no voltage drop over A at all. And that means that no power is dissipated at A. So essentially VA is 0, right? Say P equals IV, well, our V here is 0. So our power dissipated over A is 0. The question is asking how long it'll take to heat the water. Well, if there's no power dissipated over A, then it'll take an infinite amount of time because it's just not going to heat up the water. So we've answered that part of the question. That's really easy. But now we need to discuss B and C. Okay, so from symmetry, we know that the voltage across B and C is going to be the same. So that means that the power dissipated in V and C is also the same. And we can say that the power dissipated is V squared over R, or 42 squared over 6, which is equal to 294 watts. So we know the power dissipated in B or C, but what we need to know is how long we need to run our component at this power in order to generate enough energy to raise the liquid by 7 degrees. So for this, we need an equation. You may remember it as Q equals MCAT, but the energy required to raise a certain mass of a certain substance of a specific heat capacity C by a certain change of temperature is equal to mc delta T. And this will be equal to the power dissipated in our component multiplied by the time it'll take to generate that much energy. So then we can rearrange this to get an expression for time. And if we stick in the numbers, we see that it takes 100 seconds for component B and component C to raise the temperature by 7 degrees. Okay, so this next question is very similar to that one where we had to add up the resistances, but instead we have to add up capacitances. And they've been very generous in this question, giving us rules on how to add capacitances. But essentially, it is the opposite to what we do for resistors. So to add resistors in series, we would just sum them like normal, right? But for capacitors, we say 1 over the total is 1 over C1 plus 1 over C2 plus etc. And then for parallel, for a resistor, we'd say 1 over R total is 1 over R1 plus 1 over R2, etc. But for a capacitor, the total capacitance is just the sum of the capacitances, like we did for resistor in series. And that's what these rules are telling us. So that means that the easiest things to add up first are these parallel components, right? So like we did for the resistances, we need to add up the branches, and the easiest ones are these ones with these parallel components first. So the bottom branch, we add 3 in parallel and we get 3C. The second branch in series, we have C plus what these parallel ones added to, which is 2C. And then the top one, I added those in series. So the reciprocal of C plus the reciprocal of C is 2 over C, and then we take the reciprocal of that to get C over 2. So our top rung has a total capacitance of C over 2. Our bottom rung has a total capacitance of 3C, and then we just need to add these two in series now. And that would be the reciprocal of C plus the reciprocal of 2C, and then take the reciprocal of that to get 2C over 3. This is our new redraw for the 3 branches. And then we have the easy job of adding these in parallel. So we just add these up, how we would add resistors in series. C over 2 plus 2C over 3 plus 3C. Made all the denominators 6, and then add them up to get 25C over 6. Right, so this next question here is kind of a sketching question, but it requires us to understand a little bit more about capacitor. So it says a 12-volt battery, a voltmeter, an ammeter, and a resistor of 2 kilo ohms are sketched in figure A below. So this is this here. And they want us to sketch connections in order to measure the potential difference across the resistor and the electric current. So if you remember how we attach voltmeters and ammeters, in order to work out the voltage across this resistor, then we need to add this in parallel to the resistor. And in order to work out the current in the branch, we need to add that in series. So I've just done a little sketch down here of what that looks like. It looks really awkward, but that's how it is. And then they also asked us to work out what the current was. So I just used Ohm's law for that. We know the resistor has a value of 2000, and we know that the voltage is 12. So V equals IR, rearrange for I equals V over R, and we get 6 milliamps. Okay, so next it gets a little bit more complicated. It says a capacitor of 4 microfarads and a switch S are sketched in figure B. As sketched in figure B are inserted into the circuit. Sketch how the current depends on time from moment TE when the switch is moved to E, closing the circuit. So like this. Estimate the time T after which the current is not charging significantly. After time TD, much longer than T, the switch is moved to D. Sketch the current from that moment until the moment when the current is not charging significantly. Indicate on your sketch the time interval T. So for this, we need to understand a little bit about how a capacitor works. So while our circuit is connected like this, we have positive charge on this side and we have negative charge on this side. So our current is flowing like this, and we have a positive charge buildup here. And well, if we think about what's actually happening, electrons are flowing in the opposite direction, aren't they? Are building up a negative charge on the other side. So this happens at an exponentially decreasing rate, essentially. So the charge builds in a fashion so that it's exponentially decreasing, because as more and more electrons are traveling round and round like this, more and more are building up here and causing more repulsion for the rest of the electrons coming. So they start to kind of slow down and get repelled by this buildup of charge over here until it's not charging significantly anymore. So that's what's happening to our charge, but it means that our current is decreasing as the charge is building up there exponentially. So we start with our original current of 6 milliamps, and then it's getting smaller and smaller and smaller until it's essentially stagnating to 0. But it never quite reaches 0. And this is just something that you need to know, but the time that it takes for it to no longer charge significantly, we say that happens after 5 time constants. And our time constants we can find from how we define our sketch. So our current is changing with time such that it is your initial current, so in our case 6 milliamps, multiplied by e to the minus t over RC, and RC is what we call a time constant. So after 5 of those, charging is no longer significant, and our current will drop to an insignificant level. And 5 time constants was 40 milliseconds. And then the next part that they wanted us to do was to imagine that we switched the switch the other way around so that we're connected to D. So this part down here is not relevant. We had that charge buildup here where we had the negative and the positive charge there. So now our current will flow this way. So our positive charge will flow to the negative side until we have a kind of neutral buildup. And at that point, the current won't flow anymore. And this again happens gradually in this kind of like exponentially decreasing fashion. And our current is traveling in the opposite way than what we defined it in the first place. So we'd say that it's a negative current and then tending towards 0. Again, it'll slow down to essentially nothing after 5 time constants. So this next question is relating to diodes, and we're told that 2 diodes are connected to the sketch below, and they want us to sketch the current flowing between points C and D as a function of voltage applied between points C and D. So what we need to understand about diodes is that no current will flow through them until we reach a threshold voltage. And then at that threshold voltage, we can have a current flow of any value, essentially. So what that will look like for this, let's say this first diode here now. So if we're flowing this way, then until the voltage drop over this is VD, then we'll have no current. So we can see it's nothing until we reach that threshold voltage, and then we can get an increase in current, or a current of any value really. And then if we think about an opposite voltage being applied so that we have negative VD, then what's going to happen is the current is going to flow this way and go through the other diode. So the negative side of our graph will look like this. So between these 2 threshold voltages, so until it exceeds minus VD, then no current will flow. And then at that point, we will get a current in the opposite direction flow. So next, they explain that an instrument is put here and an amp is put here. And essentially, our amp will take whatever signal is sent by our instrument and amplify it so that we can understand it better. So say we have, I don't know, like a microvolt signal coming from the instrument, we probably wouldn't detect that easily, so our amplifier will ramp this up. But say we have some kind of a voltage surge from our instrument, and suddenly it sends 10 volts through. And if we are ramping that up hundreds of times, then we will get a ridiculous signal come to the amplifier and potentially break it. So what our diode system does here is it says, while we have a small voltage across our instrument and amp here, then the current will just flow normally like so. And it will just flow straight to the amp and there won't be a problem because we are underneath that threshold voltage of our diodes. So nothing will flow down here between C and D. So our path will be AC, E, F, D, B, while the voltage is small and positive. But the instance that our voltage across the instrument exceeds that VD, that threshold voltage, then we won't get a current flow down EF anymore. It'll flow down here instead and bypass the amplifier, thus not blowing it up. And then from the opposite logic, the other side, if we have negative voltages, then we'll flow this way instead. So we'll go BDF ECA. But if that negative voltage goes more negative than minus VD, then if it went through here, then we would risk blowing up the amplifier. So instead, it will take this path here across the diode and bypass the amplifier. Again, not blowing it up. So if you're interested in my written answer, then I'll just pop this here and you can pause and read what I've written down. Try and make sure my face isn't in the way. Okay, so this next question here tells us that we have two lamps in series and they tell us what the power of the lamps are when they are individually connected to this cell. And we want to know when the switch is closed, which will be brighter and why. So essentially what we really want to work out here is we want to work out what the resistance of both of these lamps are. So that when they're in series, we can know what the voltage share is like over the two. So we can individually work out the voltages of both lamps. So lamp A, if we use P equals V squared over R, we can rearrange that to get a value for resistance of 100 ohms here. And then we can do the same thing for lamp B to get 500 ohms. So when we put these values back in here, so we had 100 ohms and 500 ohms. So again, we have that similar dilemma of, okay, so we know the total voltage, but it's not shared equally between the two components. It is split, but we do know that the current will be the same over the two components. So if we look at the relationship of P equals I squared R, then from this we can say that the power is proportional to the resistance. The reason I'm not using P equals V squared over R in this circumstance is because our V is not going to be the same for both of the lamps, so we can't really compare that equation. So if our power is proportional to our resistance, then we can say that the one with the higher resistance is the one that is going to have the most power dissipated through it, meaning that it will be brighter. And because our resistance is 5 times more for B than A, then it will be 5 times brighter. Okay, so then in the next question, they asked how this would be different if it was connected in parallel rather than series. So now in this case, we can't say that the current is the same between both of them anymore, can we? Because the current splits depending on the resistance of the lamps. But we do know that the voltage across both the lamps this time will be the same because in parallel, the voltage will be the same across each branch. So in this case, we can use P equals V squared over R. And this time we see that we have a relationship that says that power is inversely proportional to the resistance. So this time, the one with the smaller resistance is going to be the brighter one. So that means A is going to be brighter. And because our resistance is 5 times less, it means it will be 5 times brighter. So this next part of the syllabus moves on a little bit from circuitry and is talking more about electrostatic forces and the forces between point charges. So this question says, an electron initially at rest is accelerated by a potential V in a vacuum and then travels horizontally in a region of space where there is an electric field, E, and a magnetic field, B. The fields are aligned such that the electron is subjected to a force EE upwards and a force EVB downwards, where E is charge on the electron and V is its velocity. So the electric field strength is 1,000 volts per meter. Our magnetic field strength is 1 times 10 to the minus 5 Teslas. What is the value of the initial accelerating voltage for the electron to continue flying undeflected? So what we're saying is we have this electron that's moving at some speed v, and it has some force pulling us up and another force pulling us down. And in order for it to continue on a straight trajectory, what voltage v do we need to keep it in check? So we know that our force up is the E and our force down is EVB. So we can equate these to get a value for the velocity of our particle. So what that says is that we need to accelerate our particle to this specific velocity in order for the forces to balance correctly. So at this point, we need to know how much accelerating energy, essentially, do we need to put in to get this specific kinetic energy. So the energy put in by accelerating a particle through an electric field would be the charge of this particle multiplied by the field strength. So then we can equate that to our kinetic energy and rearrange to get a value for our electric field strength. Okay, so this next question, we can assume that the electrostatic potential energy of two positively charged particles with these charges separated by a distance x is given by this equation here. So just to reiterate, this is the electrostatic potential energy. So this is an energy term here. And they say two charged particles are placed a distance d apart from each other. One has charge plus q and mass m, whilst the other has charge plus 2q and mass 2m. The charges are initially held stationary, but are then released. Find an expression for the maximum speed of the particles with mass 2m. So what's happening are we have this particle here with a positive charge and this particle here also with a positive charge. So they're going to be repelled from each other. We'll call this V1 and V2. And we want to know what the maximum possible speed V2 is. So the first thing that we want to do is we want to look at conservation of momentum. So the momentum before is 0 because they were both still. And then the momentum afterwards, they're moving in opposite directions. So we have mass V1 minus 2 times mass V2. And then that gives us an expression for V1 in terms of V2. And then the next thing we want to do is conservation of energy, because we're essentially converting all of this potential energy into kinetic energy if we were to say that V2 will be as fast as possible. So that implies that all of the energy was transferred to kinetic energy. So if all of it was converted to kinetic energy, that means that our potential energy is equal to half m V1 squared plus half 2m V2 squared. And we had a little expression for V1, so we can replace that to get an expression where the only unknown is V2. And then we can rearrange that to get a final expression for V2. Essentially, that was conservation of momentum and conservation of energy. So this next portion of the syllabus refers to the photoelectric effect. And I won't lie, I could barely find any questions about the photoelectric effect. But the photoelectric effect is essentially if we have a metal, our metal will have some intrinsic work function related to it. And this work function is essentially the amount of energy that the minimum amount of energy that we need to fire at this piece of metal in order to release photons. And any leftover energy, so say we have a work function of and honestly, these values are just not real, but 5 joules, and say we supply 10 joules, then it took 5 joules to get the photons out of the metal. Then we have a leftover 5 joules to accelerate this particle. So this question here says that we have light of wavelength 625 nanometers shine onto a metal surface with a work function of 1 electron volt. Electrons are emitted from the metal. And they want to know what the maximum speed of the emitted electrons is. So first of all, we need to work out how much energy was supplied by firing this beam of light of wavelength 625 nanometers. So we need to know the all-important equation of E equals HF and C equals F lambda, and then rearrange those together to be E equals HC over lambda. And we can work out how much energy was supplied by the shining light. And this is 18 over 625 times 10 to the minus 17, which is a really weird number, which is a very, very small number, but reasonable. And then next, we're told that the amount of work it takes to release the electron is 1 electron volt. So how we convert electron volts to joules is that we multiply this by the charge of an electron. So that would be 1 times 10 to the minus 19. And we can see that these values make sense because this is a larger value than this, and we are told that photons are released. So this amount of energy supplied needed to be greater than the work function. So the energy left over is the difference between these two values, so 1.28 times 10 to the minus 19. And if all of that leftover energy is converted to kinetic energy, then we can say that half mv squared is equal to that, and rearrange to get a value for V. Okay, so the next part asks us, the electrons are then accelerated through a potential difference of 5 kilo electron volts towards a fluorescent screen. What is the final speed of the electrons when they hit the screen? So we have, this time we have that leftover kinetic energy that we worked out before, this 1.28 times 10 to the minus 19. And then we also have an energy put in from accelerating. So this is our 1.28 times 10 to the minus 19 joules here, plus this 5 kilo electron volts, or 5 times 10 to the 3 times the charge of an electron. And that is our new total energy. So our new total energy was 8 times 10 to the minus 16. And then we can do the same jam again of saying, well, all of that is converted to kinetic energy. So half mv squared is 8 times 10 to the minus 16, and rearrange for V. And we get an even bigger speed. So I couldn't actually find any more questions relating to work functions and the photoelectric effect, but I thought kind of a similar tangent would be these energy level quantization questions to do with hydrogen. So what this question says is the energy levels of the electron in a hydrogen atom are characterized by quantum number n. So En is minus hcr over n square, where we have different constants. And they want us to state a formula that relates the wavelength of light to Planck's constant, to the speed of light, and energy, which is the energy of a photon. So we've just stated that in the previous question, E equals hc over lambda. Next, they say let P and Q be quantum numbers of the upper and lower energy level of an electron transition in hydrogen. And they want us to find a formula that relates the wavelength of light emitted in such transition to P and Q. So we can say that the energy at level P is EP, which is minus hcr over P squared. And then our energy at level Q is minus hcr over Q squared. So the amount of energy released dropping from the higher one to the lower one would be the change in these values. So minus hcr over P squared minus hcr over Q squared. Rearrange these to get hcr over Q squared minus hcr over P squared. And then we want to say that all of that energy is converted to a photon energy, I suppose. So we can equate hc over lambda, which is what we said in the first part, to this expression here, cancel our hc's, and then we can get an expression for lambda, which is what they wanted. Okay, so this last part of the question is where it gets a little bit head spinny a bit. But they're saying for each of the 3 hydrogen emission line sets shown in the table, identify the quantum number of its lower energy level Q. Each set column of 5 emission lines has the same lower energy level. The first column shows the quantum number of the upper energy level Q relative to the lower level. And we can assume that P is less than 6. So they've kind of given us too much information in this question. We only really need this first line here because this tells us what the wavelength of our first emission is technically. So our drop from the lower energy level that we're considering. So this first column is all that's useful because that's what tells us about the drop from this value here that we want to know from the one above that, essentially. So we can make our own little table here. We know that P is, well, I think this little thing that they told us here is a bit questionable, but we'll say it less than or equal to 6. So we can count up Q so that we have some values of Q. So 1, 2, 3, 4, 5. And if our value of Q is 1, then our next level P will be 2. And if our value Q is 2, then the one above it will be 3, etc. So we have P as 2, 3, 4, 5, and 6. And then using our equation from the previous part, we can come up with a value for the wavelength for the drop from one to the other. So our wavelength for the first one, I calculated to be 121.5 nanometers. The next one, 656.1 nanometers, and so on and so on and so on. And then we can relate back to this first column up here to see which Q they refer to. So this first one here, 121.57, well, this is what we got for when Q was 1. So set A refers to Q being 1. Our next one, 4,051 nanometers, is close to what we got for Q as 4. So Q for our set B is 4. And then 7,460 is what we got for, or close to what we got for Q being 5. So for set C, Q is 5. And that's our answer. And now we have a slightly easier question relating to these energy levels of hydrogen to finish. And they gave us an expression for the energy levels of hydrogen here, a different one to previously, don't really know why. But we are only talking about changes between the ground state n is 1 and n is 10. So they want us to tell them what the shortest wavelength of light emitted would be. So if you've seen these hydrogen energy levels before, you'll know that they kind of look something like this. So the changes in energy level get smaller and smaller for the higher levels. So this means you get the largest energy released dropping from 2 to 1, and a lower energy drop from, I don't know, let's say like 5 to 4. I don't know if that was actually 5 and 4. And in this first part here, they want us to work out what the shortest wavelength of light emitted is. And a short wavelength implies that it's high energy. So a lot of energy means that it's dropping from the lowest possible energy levels. So we want to work out the energy change between the two lower energy levels. So the energy at n is 2 would be r over 4, and the energy level at n is 1 would be r over 1. So we can work out the difference between these to be 0.75 r. And then if we equate that energy released to the photon energy, then we can rearrange this to get an expression for lambda. And they've asked us to just leave it in terms of the constants. And then next, they want us to work out the longest wavelength emitted. So that would be where the smallest gap is, right? So the smallest gap would be between n is 10 and n is 9. So we find out the change in energy between 10 and 9, equate that to hc over lambda again, and we'll get an expression for our wavelength. And then finally, they say how many emission lines would be observed. So if we think about what that looks like, then where do we have emission lines? Well, between n is 2 and n is 1, we have one emission line. Between n is 3 and n is 2, we have 1, 2, and this first one here. But that can be counted in the first one. So for n is 3, we have 2 new emission lines. At n is 4, we have 1, 2, 3, and all of these ones that have already been. So n is 4, we have 3 new emission lines, and I'm sure you can see at this point there's a pattern that for level n, we have n minus 1 new emission lines. So to work out how many emission lines in total there will be, then we just need to add up 10 minus 1 plus 9 minus 1 plus 8 minus 1 plus 7 minus 1, etc., etc., etc. So that would be adding 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, which comes out to 45. So we have 45 emission lines. And that's all that question asks for. So we've come to the end of this topic. I hope it's been helpful for you. And in the next episode, I will be talking about the natural world. I'll see you there.